Okay guys, good morning. So today's lesson is going to be a little different, just in the sense that we're not going to do a do now, just because it's a lot of discussion today, right? It's a lot of vocabulary, a lot of discussion. So today's probably the only day, or one of the only days we'll bypass our do now, and we'll just kind of cut right to the chase here. So it says, how do we classify and compare real numbers? Now, we're not going to do so much of the comparing, at least not today. We're going to focus mostly on classifying. So classifying means to give something a name or a description, or to categorize it. So our real numbers basically can be broken down into two groups, right? We've got our rational numbers and we've got our irrational numbers. Now, for the most part, right, we're used to dealing with rational numbers. Now, there is one very famous irrational number that we've worked with, hopefully somewhat extensively, though we're not going to really do too much of it this year. But that's basically the main distinction. And then once we break down into rational and irrational, our rational numbers can break down into some kind of subgroups. So the important thing to understand is that a rational number can be written as a fraction. So 5 is a rational number, right? Because we can write 5 as 5 divided by 1. And so is something like -3. Okay, I can write that as -3 divided by 1. Obviously, something like 1/4 doesn't need any conversion because it's already a fraction. And we're going to say, well, what about other decimals, right? What about 3 and 7/10? Well, I can write this as 3 and 7/10, but I can also write it as 37/10. Okay, so I can write a number like 5 or like -3 as a fraction, right? We'll also come to know those as integers. 1/4 already is a fraction. A standard terminating decimal also can be written as a fraction. Terminating means it ends, right? In other words, 3.7, I have no decimals after the 7, right? And if I had another decimal like 3.75 or 3.738, I could convert those into decimals too, right? Just to give you an example, this is 3 and 78 hundredths, so I can write this as, let's say, 378 out of 100 if I wanted to. Now we're going to say, well, what about those other types of decimals, right? What about those, what we call repeating decimals, 0.33333333, ... Well, usually we use what's called bar notation for those. Now, what do we know about this specific decimal? Well, hopefully we know that it's equal to 1/3. Now, what about something like, I don't know, 0.57 repeating? Could we write that as a fraction? Absolutely. There's a very simple algorithm involving like a 1 or 2 step equation that would allow us to write that as a fraction. Not really worth getting into right now, just because it takes a little bit of time to learn, but we need to understand that any of those repeating decimals can be written as fractions. Now, what can't we write as a fraction? Well, we can't write as a fraction a decimal that doesn't repeat. Right? Something like that. How can I write that as a fraction? I can't. It's got no place value. After the 0 maybe comes a 7, and after that maybe comes a 4, and then maybe a 2. There's no way I can write it as a fraction without defined place value. So that's one type of irrational number. Now, what's another type of irrational number? Well, the most famous irrational number is pi. Why can't I express, and don't tell me 22/7, that's just an approximation. Now, why can't I express pi as a fraction? Well, because pi is a decimal that, just like the one I have over here, never terminates and never repeats. So there's no way I can write it as a fraction, right? 3.14159.2653589, and then it goes on for billions and billions. It goes infinitely, right? Well, I think computers can calculate maybe 6 or 10 billion of them, but we know that it's infinite. And the other type of irrational number is the square root of a non-perfect square. What's the square root of 10? I don't know. Right? I know that it's bigger than 3 and it's less than 4. I know it's probably somewhere in the neighborhood of 3.1, between 3.1 and 3.2. But if I put this into a calculator, it's going to fill my screen up with decimals and then it's going to stop because the calculator can't handle anymore. But in reality, this is exactly the same as pi, which is exactly the same as this. It's what's called a non-terminating, non-repeating decimal. Those are the only types of irrational numbers that we will see. Okay? Pi is the biggest one. Square root of a non-perfect square, and just that random kind of mishmash of numbers after a decimal with no discernible pattern. Now let's break that down a little further. Okay, so this is really the bulk of the lesson here is the vocabulary. Okay, so I want you guys to pause it, and I want all of this in your notes. Okay, when I do my note check, That's one of the things I'm going to be looking for when we check the notebooks. Okay, so make sure that you got this in your notes, and I can start talking about it. So this is our breakdown here, right? I've got my rational and I've got my irrational. So a rational number is exactly what I just described. It can be written as a fraction. All right, irrational numbers cannot be written as a fraction, and it says it does not terminate and it does not repeat, right? So like, 6/10 as in 0.6, that terminates, the decimal stops. 0.33333333, that repeats, okay? So that's okay, that's a fraction, that's 1/3. A decimal that doesn't terminate or repeat is going to be irrational. So most numbers we see are going to be rational. Now, within the rational numbers, you also have these three subgroups. All of these numbers are going to be rational. Now, the whole numbers and the counting numbers are almost exactly the same. So if you look at the whole number says the number 0, 1, 2, 3, 4, 5, 6, 7, all the way out to infinity. Now, what's different about the counting numbers? They don't include 0. Why don't they include 0? Because you never count 0 of something, right? If you don't have anything, right? I always use the example of, $0 million bills in my pocket, right? And somebody said, how many do you have? I wouldn't say, well, let me go count them. I'd say, there's none of them, okay? So we're not going to use 0 as a counting number. 0 is a whole number. Now, what do we know about the integers? Well, they're kind of hard to define, right? We say they're the counting numbers, they're opposites, and 0. So basically what you'd see on a standard number line, if the number line didn't have fractions and decimals. So integers do not include fraction and decimal quantities unless they can be simplified to be an integer, right? So 0, 1, 2, 3, 4, 0, -1, -2, -3, -4, those are integers, right? Whole numbers, opposites, and 0. So most of what we're going to do today is really just going to be classifying different types of numbers. All right, so let's take a look at something. Now, what I'm going to do, and I suggest you do this for your homework as well, is I'm going to make a key. I'm going to say R equals rational. I'm going to say IR equals irrational. I'm going to say I equals integer. I'm going to say C equals counting. And W equals whole. So rather than write out the words for everyone, I'm going to use my key. So if you want to do this for your homework, again, that's fine. Just make sure you put the key. If your key is different than mine, that is absolutely fine, but I do need to see a key. So I'm going to look at the first one, -15. Now, one thing we need to understand is every number has to be either rational or irrational. If it is irrational, it will only be irrational. If it is rational, it's possible that it has other classifications. So let's look at -15. Is -15 a whole number? No, because whole numbers and counting numbers have to be positive. I mean, a whole number can be 0 or positive, and a counting number is positive. Is -15 an integer? It is. So -15, we're going to classify it as an integer. And again, every number must be rational or irrational. It is rational. Could I write it as a fraction? Absolutely. -15 with a denominator of 1. So it's an integer and a rational number. What about 3 2/10? Well, I said before that integers are what you'd see on a traditional number line, meaning no decimals. So that's not going to be an integer. It's not going to be a counting number or a whole number, right? If we can go back to our vocabulary, right? My counting and my whole numbers only include positive integers, and the whole numbers include 0. So what kind of number is this? Well, 3 2/10 is 32/10. That certainly could be written as a fraction because 3 2/10 is a terminating decimal, so I'm going to call that rational. How about number 3? That's the square root of a non-perfect square. I don't know the square root of 31. If I try to do square root of 31, it's going to fill my calculator with decimals with no pattern. That's an irrational number. How about -4.5? Well, that should be an easy one. -4.5 as an improper fraction is -9/2. Well, that's a fraction, right? And specifically a fraction where the numerator and denominator are integers. So I don't think I mentioned that part before, right? Because you could say, oh, well, pi could be written as pi over 1. Well, no, because that's not an integer. So I should have been more specific before. So -4.5 is -9/2. That's a fraction, so it's rational. Now this one's going to be an interesting one, right? The square root of 64. Well, I know the square root of 64 is 8. Now, technically, it can also be -8 if you want to get fancy, and we'll talk about that later on in the year. But for now, let's say the square root of 64 is 8. Well, 8 is a whole number, and it's a counting number, and it's an integer, and all of those make it rational. So some of these numbers will have multiple classifications. Let's take a look at 6, 3/8. That's not a whole number. It's not a counting number. It's not an integer. It's a fraction, so that should be easy for us to classify it as rational. The next one, it looks like 3.656565 repeats. So I can call that 3.65 repeating. Now we said any repeating decimal can actually be expressed as a fraction. That's a rational number. Let's look at number 8. That's that big mess of a decimal, right? There's no pattern, there's no repetition, it's never going to repeat. If it never repeats, I can never establish place value. That's an irrational number. Number 9, -3 and 487 thousandths. Okay, that's got the definite place value, right? That's a terminating decimal. I could express that as -3,487 thousandths out of 1,000. That's a nice clean fraction. That's a rational number. Certainly not going to be an integer, a counting, or a whole number, because none of those should have decimals. And our giveaway right here. I see the pi symbol. I know that immediately that's going to be irrational. So we're going to do something else, kind of a little sidebar here that I like to do in class. I don't know how well it's going to translate remotely. I'm hoping it goes well. But this is what I want you to do for the homework. So you're going to refer back to the slide for the homework. I didn't deviate it very much. I kept the homework very similar to these 10 questions. So make sure you've got this in your notes, and this is going to be your reference or your framework for the homework. All right, so let's take a little sidebar here. So thinking outside the box a little bit. Reasonable domains and ranges. Now, domain, if we're talking about an equation that has x and y, which we will a little bit later on, domain is the x and range is the y, but we're not really getting too much into that. What set of numbers would you use? Okay. The number of humans in this room. Okay, so not the room that I am in currently. Let's imagine, if you will, that we were in class, right? In my penthouse room 512 up on the 5th floor, and the number of humans in our classroom. Well, what do we think? Well, it's possible that there is maybe just me. It's possible that there's 9 or 10 of us. It's possible that there's a full house and there's 30 students plus me. I don't think there's going to be a fractional amount of us, right? I don't think there's going to be 3 2/3 people in my room. So I'm going to say that the number of humans in my room is going to be an integer. And then I'm going to think about that and I'm going to say, does that make sense? There's an integer number of us. So there could be -7 of us. And we realize that that's a little silly. So I'm going to say, well, an integer is not really appropriate. It can't be any integer. What we can say is any whole number or any counting number, right? It's possible that there's no one in the room. It's possible that there's 1, 2, 3, 4, 5, 6, 7, all the way up, right? So that's what I'm talking about when we're talking about thinking outside the box, right? Can we say a rational amount? No, we'll talk about that in a little bit. But again, think about, you know, if I say a rational number, that includes negative numbers, and it also includes decimals and fractions. So we're not going to say rational. Let's talk number 2, the number of ounces in my water bottle. So let's imagine again, we're in my classroom, and I'm holding up a water bottle that is not empty. All right, it may or may not be full, but it is not empty. How many ounces are in that water bottle? Okay, let's look at what we did for number 1, right? A whole number. Well, I don't know about that. You know, if my water bottle, I have a pretty big water bottle, let's say it's 32 ounces, I'm not that good that I can take whole number sips, right? Each sip is not going to be 1 ounce or 2 ounces. I may take a sip that's 2/3 of an ounce. I may take 5/7 of an ounce. I may drink pi ounces. It's possible. I may drink radical 7 ounces. It's a little odd to think of it that way, but it's possible. So how many ounces are in my water bottle? I'm going to say it's going to be a rational number. And I'm going to go a little bit further than that, and I'm going to say it's going to be a positive rational number. Right? If I say, hey guys, there's a rational number of ounces in my water bottle, you're going to say, really? You have -3 pi ounces? And I'm going to say, you're right. That's not correct. Now, I try to go through scenarios that I would go through in class, unfortunately, without a class in front of me. Okay, when I'm do lessons like this. All right, so I'm going to say, well, it could be a rational number. Certainly, it could be a fraction, right? I could have half an ounce in here, but it can only be positive. Okay, again, because I said it wasn't empty. Number 3, the temperature in a random part of the world right now. All right, so there's some places that are pretty hot. There's some places that are pretty cold. So this is going to be similar to what I did for number 2, except it doesn't have to be positive, right? If we go to somewhere in, in Antarctica where it's, negative 60, negative 70, maybe over, as cold as negative 120, I think, certainly the temperatures could be negative. So now we're just talking rational. Right? Is it going to be exactly negative 35 degrees? No, right? It's almost impossible that, if you had a very precise thermometer that went out to like maybe 10 decimal places, it's almost never going to be an exact amount, right? What's the temperature at right now? Well, my phone, my Weather Channel app says it's 83, but it's really 83.156784002 if you want to go out enough decimal places. So we're really talking about a rational number there. All right, so let's get back to kind of the meat of the lesson here. So this is your homework. So for each of these, I'm not asking you to do much, right? You're going to write out the number, and then I suggest you use a key. It does not have to be the same as my key. You could probably come up with a more creative one. But if you'd rather write, rationally, integer whole, that's fine. But that's what I want you to do. So it should look, if you use a key, very similar to this. So just to give you an example, right? Number 1 is just a rational number. Number 2, since it's negative, means it can't be a counting or a whole number, but number 2 would definitely be an integer. It would also be a rational number. And number 3, we know the square root of 36 to be 6. So that's going to be a whole bunch of things, right? It's a whole number, it's a counting number, it's an integer, and it's rational. All right, so that's what I'm looking for with the homework. As always, guys, any questions, comments, concerns, we'll talk about it on Google Classroom.